Welcome. Just before the semester starts, I want to wrap up two things, and one of the topics which I thought is already finished is the QR part, but there is something I've not mentioned yet, namely that you can deform things into the complex, which is very exciting to me, that kind of complex symmetries come in quite naturally. And so this is all in the context of analytic index functional analysis, spectral properties. The Dirac matrix here can be deformed in its isospectral symmetry space. This is not a group, but it has a natural flow on it, lots of flows on it, commuting flows on it. It's like the total story. And what happens is also interesting. I update that paper also with graphics again of the inflation, what actually happens here. Whatever you're doing, you get first kind of a relatively fast start where this D becomes, gains a diagonal part, and then in the end this diagonal part will dominate. And the side diagonal part is kind of like the electromagnetic part. I call the diagonal part the dark energy part. So this is an interesting kind of mathematical story, purely mathematical story, but it involves the QR decomposition. And I have to tell you one adventure I had, and actually that was quite a problem during the search for the relation between this and the QR decomposition. I first thought it's wrong, and one of the reasons why I first thought it's wrong is that mathematica quite cruelly takes in the QR decomposition. First of all, that's something which is, you can understand that the Q is actually the transpose matrix. That's no problem. You see that immediately when you start, but what you don't see immediately is that the R is sometimes diagonal with positive entries. Sometimes the signs of the diagonal parts change. That completely messes up the relation, and sometimes it just doesn't work. And so what I did, I made a hack in the first version, which is also on the archive. I just looked only at the n minus 1 times n minus 1 matrix and kind of hacked it like that. And then in last Sunday I changed this by introducing this diagonal matrix E, which takes the signs, and then fixing the QR decomposition like that. I decided yesterday to reprogram that completely from scratch, and like we teach it in school, right? The QR decomposition. So what you do is, first of all, so you read it like that. You start with the first column vector of A of a matrix. You take the first column vector of a matrix, then you normalize it. What you take is the next entry, the next column entry, and you take away the projection onto the space which you have already produced. That gives you a new vector. It's not yet normalized. That's the normalized vector as the next column. And then you go through the entire matrix until you have built up the whole Q matrix. And then the R matrix can be just obtained by multiplication. So that's a one-line implementation of the QR algorithm. So it's, first of all, it's very transparent, and now I'm happy. It's actually shorter even than the code with a hack. Now, another thing I'm wrapping up is this story I told before about the curvatures which are on the, higher dimensional parts of space. So this is actually belongs to this topological part of the story, Atiah-Singer kind of philosophies. You have these two indices and they are the same, they are Euler characteristic. Here you think about this differently, not using spectra, but you think about it using energies. And that's justified with the energy formula I proved once, 2016, that you can think about Euler characteristic as an energy. Because what happens is you can write it as a sum of green functions, gxy entries, and gxy is the potential energy between x and y, parts of space. So it's kind of a natural way to think about this, and if you take these chunks of energy and you put them onto the zero-dimensional part, then you get the curvature which you have in differential geometry. Differential geometry, I'm starting to teach this now, so that's kind of an interesting story, like Gauss-Bonnet. And this can be done by pushing things on higher dimensional parts, like the facets, for example. I claimed once that for odd dimension manifolds this curvature is constant zero. That's not true. I mean, just make experiments and you see it's not true. So that's another update, and I will post that note also this weekend. I have to get this off, because otherwise I will forget about it. So these are the two remarks I wanted to make.